Hello students, in this lecture we will discuss about the available energy. As you all know that energy exists in variety of forms. The sources of energy are broadly divided into two groups, high grade energy and low grade energy. The conversion of one high grade energy to another high grade energy, as well as the conversion of a high grade energy to low grade energy, is exempted from the limitation of the second law. It means that conversion of, or you can say the complete conversion of high grade energy to another high grade energy, as well as the conversion of high grade energy into low grade energy, is possible, whereas the full conversion or complete conversion of low grade energy into high grade energy, or you can say shaft work, is not possible. The second law comes into picture and it says that the complete conversion of low grade energy into high grade energy is not possible. Now, if we talk about the example of high grade energy and low grade energy, then mechanical work, electrical energy, water power, wind power, kinetic energy of a jet, or tidal power, they are basically the examples of high grade energy. Heat or thermal energy, heat derived from nuclear fission or heat derived from combustion of fossil fuels, are basically the examples of low grade energy. The bulk of high grade energy in the form of mechanical work or electrical work is obtained from sources of low grade energy, such as fuels, through the medium of cycle heat engine. Now, the complete conversion of low grade energy, heat, into high grade energy, shaft work, is impossible by the virtue of second law of thermodynamics. That is what we have come to know till now. The part of the low grade energy which is available for conversion is known as available energy, whereas the part according to the second law must be rejected is known as unavailable energy. The maximum work output obtainable from a certain heat input in a cyclic heat engine is called the available energy, or the available part of the energy supplied. The minimum energy that is rejected to the sink as per the second law is called the unavailable energy or unavailable part of the energy supply. Now we are discussing the available energy for a cyclic heat engine. Now the cyclic heat engine is basically absorbing the heat from a source which is maintained at temperature T1. This cyclic heat engine is doing a certain amount of work and rejecting Q2 amount of heat to the sink which is at temperature T2. So now, for a given value of T1, the efficiency of a reversible cycle will increase with the decrease of T2 as shown in the formula of efficiency. The formula of efficiency is 1 minus T2 upon T1. So, if we decrease T2, then efficiency will increase for the given value of T1. Now, the lowest practicable temperature of heat rejection is the temperature of the surroundings, T0. If we are interested in increasing the efficiency of the cycle, so what is the temperature to which we can decrease the temperature of T2? That is T0, that is temperature of surroundings. So the maximum efficiency of the cyclic heat engine can be 1 minus T naught upon T1, and the maximum work obtainable will be 1 minus T naught upon T1 into Q1, where Q1 is the heat supplied. Let us consider a finite process xy in which heat is supplied reversibly to a heat engine. Taking an elementary cycle, if del Q1 is the heat received by the engine reversibly at T1, then the maximum work obtainable is equal to 1 minus T naught upon T1 into del Q1, and that becomes del Q1 minus T naught upon T1 into del Q1. Now for the heat engine receiving heat for the whole process xy and rejecting heat at T naught as shown in the diagram, the maximum work obtainable from the limit x to y is equal to del Q1 integrated from limit x to y minus T naught upon T1 into del Q1 integrated from the limit x to y, and that is basically the available energy. So the maximum work or the available energy is equal to Qxy minus T naught into Sy minus Sx, because in the upper equation T naught was T naught being a constant was taken out of the sign of integration, and the del Q1 upon T1 when integrated from x to y, it basically came out to be the change of entropy, that is Sy minus Sx. So the unavailable energy is equal to heat supplied minus available energy, or you can say maximum work. So unavailable energy is equal to T naught into Sy minus Sx. So you can say basically that unavailable energy is the product of lowest temperature of heat rejection and the change of entropy of the system during the process of supplying heat. The available energy is also known as exergy, and the unavailable energy is also known as energy, ANERGY. Now we will discuss decrease in available energy when heat is transferred through a finite temperature difference. So we take up a Carnot cycle. As you know that Carnot cycle is a reversible cycle. So here it is being assumed that there is infinitesimally small temperature difference between the heat source and the working substance when it is absorbing heat. Now for this, the amount of heat supplied will be equal to T1 into delta S, and the amount of heat rejected will be T naught into delta S, and T naught is the atmospheric temperature. So the maximum work obtainable or the available energy will be T1 minus T naught into delta S. Now here we assume that heat Q1 is transferred through a finite temperature difference from the reservoir or source at T1 to the engine absorbing heat at T1 dash lower than T1. Here we have assumed that there is a temperature difference between the heat source that is supplying energy and the working fluid that is circulating in the cycle. So Q1 is equal to T1 delta S is equal to T1 dash delta S dash. Here we have assumed that in this case also the same heat is being supplied as it was done in the case of the reversible case or the Carnot cycle, as we discussed on the last slide. Now T1 is greater than T1 dash, so we can infer that delta S is greater than delta S dash. Now the amount of heat rejected in this case when heat is transferred through a finite temperature difference, it will be T naught into delta S dash. Since delta S dash is greater than delta S, therefore Q2 dash will be greater than Q2. So W dash, which is the maximum work obtainable or the available energy when heat is transferred through a finite temperature difference, will be Q1 minus Q2 dash. So that becomes T1 dash delta S dash minus T naught delta S dash. And W is the maximum work obtainable or the available energy in the case of reversible cycle, when there is infinitesimally small temperature difference between the energy source and the working fluid. So in that case, work or available energy is equal to Q1 minus Q2, and that is T1 delta S minus T naught delta S. Now we can conclude that W dash is less than W because Q2 dash is greater than Q2. Now we want to find out what is the loss of available energy due to irreversible heat transfer through finite temperature difference between the source and the working fluid during the heat addition process. That is obtained by subtracting W dash from W, and that will basically yield us Q2 dash minus Q2 because Q1 is same for both the cases, means same heat is being supplied for both the cases. So that basically yields us T naught into delta S dash minus delta S. So decrease in available energy is T naught into delta S dash minus delta S. The decrease in available energy is thus the product of the lowest temperature of heat rejection and the additional entropy change in the system while receiving the heat irreversibly compared to the case of reversible heat transfer from the same source. Now we will discuss the available energy that can be obtained from a finite energy source, that is a thermal body. Let us consider a hot gas of mass mg at temperature T when the environmental temperature is T naught. Let the gas be cooled at constant pressure from state 1 at temperature T to state 3 at temperature T naught, and the heat given up by the gas Q1 be utilized in heating up reversibly a working fluid of mass MWF from state 3 to state 1 along the same path, so that the temperature difference between the gas and the working fluid at an instant is 0, and hence the entropy increase of the universe is also 0. The working fluid expands reversibly and adiabatically in an engine or turbine from state 1 to state 2, doing work WE, and then rejects heat Q2 reversibly and isothermally to the initial state 3 to complete a heat engine cycle. Now Q1, that is heat given out by the hot gases, or you can say the heat absorbed by the working fluid. So that is equal to mg Cpg into T minus T naught, and also MWF into CPWF into T minus T naught. So this concludes that mg Cpg is equal to MWF into CPWF. Now the entropy change of the hot gas will be equal to del Q upon T when integrated from T to T naught. So since the hot gases are supplying heat to the working fluid at constant pressure, so del Q will be mg Cpg dt as written above also. So now the integration of this term will yield us mg Cpg into ln of T naught upon T. Similarly, we find out the entropy change associated with the working fluid, and that comes out to be MWF into CPWF into ln of T upon T naught. Now out of these two terms, one is negative and one is positive. And since mg Cpg is equal to MWF CPWF, the addition of these two terms will yield us the value 0. That is, the entropy change of the universe will be 0. Now the amount of heat rejected to the sink is equal to T naught into delta S WF. Now this is equal to T naught into MWF into CPWF into ln of T upon T naught. Now the available energy will be equal to Q1 minus Q2. So that becomes mg CPG into T minus T naught into T naught mg CPG into ln of T upon T naught. So 8.4 equation gives us the final expression for the available energy that can be obtained from a finite energy source, that is a thermal body. Now we are going to discuss a very important topic, quality of energy. It is the second law that assigns quality index to the energy. Let us assume that a hot gas is flowing through a pipeline as shown in the figure, and the hot gas is entering from the right side and exiting from the left hand side. Due to heat loss to the surroundings, the temperature of the gas decreases continuously from the inlet at state A to the exit at state B. Although the process is irreversible, but we can assume a reversible isobaric path between the inlet and exit states of the gas. Now for the infinitesimally reversible process at constant pressure, we can say the change of entropy is mCp dt upon T. So we rearrange the terms and we get the expression as dt upon ds is equal to T upon mCp, where m is the mass of the gas flowing and Cp is the specific heat. The slope dt upon ds depends upon the gas temperature T. As T increases, the slope increases, and if T decreases, the slope decreases, which will become clear in the diagram on the next slide. So here you can see on the TS diagram that as the temperature increases, the slope increases. That is, dt by ds increases, and if T decreases, the slope decreases. Now let us assume that Q units of heat are lost to the surroundings as the temperature of the gas decreases from T1 dash to T1 double dash, T1 being the average of the two. Then heat loss, that is Q is equal to mCp into T1 dash minus T1 double dash is equal to T1 delta S1. Now available energy lost with this heat loss at temperature T1 is the heat lost minus the unavailable energy lost along with this heat loss. So this becomes W1 is equal to Q minus T naught delta S1. So this available energy is lost with this heat loss. Means had this heat not being lost, we could have obtained this much of maximum work, that is W1. Now when the gas temperature has reached temperature T2 and T2 is less than T1, we assume that same amount of heat loss is there at this section as the temperature decreases from T2 dash to T2 double dash, and T2 is the average temperature of the gas. So then we can say heat loss Q is equal to mCp into T2 dash minus T2 double dash, which is equal to T2 into delta S2. So available energy lost with this heat loss at temperature T2 is W2 is equal to Q minus T naught delta S2. Now from the equation 3.6 and 3.8, as the temperature T1 is greater than T2, we can say delta S1 is less than delta S2. So we can say from equation 3.7 and 3.9, W1 is greater than W2. So the loss of available energy is more when heat loss occurs at high temperature T1, when the same heat loss occurs at the lower temperature T2. Therefore, a heat loss of 1 kilojoule, say 1000 degrees Celsius, is more harmful than the same heat loss of 1 kilojoule at 100 degrees Celsius. So sufficient insulation must be provided for high temperature fluids. Means when temperature are quite high than the atmospheric temperature to prevent the precious heat loss. This may not be so important for low temperature fluids if the temperature are very close to atmospheric temperature, since the loss of available energy from such fluids would be low. Similarly, insulation must be provided sufficiently for the low temperature fluids, that is when the temperatures are sufficiently lower than or considerably lower than the atmospheric temperature to prevent heat gain from surroundings and preserve available energy. The available energy or exergy of a fluid at a higher temperature T1 is more than that at a lower temperature T2 and decreases as the temperature decreases. The second law therefore affixes or assigns a quality to energy of a system at any state. The quality of energy of a gas at 1000 degrees Celsius is superior to that at temperature 100 degrees Celsius, since the gas at 1000 degrees Celsius has the capacity of doing more work than the gas at 100 degrees Celsius under the same environmental conditions. An awareness of this energy quality is essential for the efficient use of our energy resources and for our energy conservation. The concept of available energy or exergy provides a useful measure of the energy quality. The available energy of a system decreases as its temperature or pressure decreases and approaches that of the surroundings. When heat is transferred from a system, its temperature decreases and hence the quality of its energy deteriorates. The degradation is more for energy loss at higher temperature than that at a lower temperature. Quantity wise, the energy loss may be the same, but quality wise, the losses are different. While first law states that energy is always conserved quantity wise, the second law emphasizes that energy always degrades quality wise. When a gas is throttled adiabatically from a high to low pressure, the enthalpy, that is energy per unit mass, remains the same. But there is degradation of energy or available work. The same holds good for pressure drop due to a friction of a fluid flowing through an insulated pipe. If the first law is the law of conservation of energy, the second law is called the law of degradation of energy. Energy is always conserved, but its quality is always degraded. Now here we want to prove that maximum work is done in the case of a reversible process. Let us consider a closed stationary system undergoing a reversible process R from state 1 to state 2, interacting with the surroundings that is maintained at the temperature and pressure T0 and P0 respectively. Then by first law, we can say for the reversible process, QR is equal to U2 minus U1 plus WR. So QR is the heat transfer for the reversible process and WR is the work done for the reversible process. Now, if the process were irreversible, shown by the dotted curve, connecting the same equilibrium states, then this first law can be expressed as Qi is equal to U2 minus U1 plus Wi for the irreversible process, or you can say irreversible change of state. Now, Qi is the heat transfer for the irreversible process and Wi is the work done for the irreversible process. U2 minus U1 will remain same for the reversible as well as irreversible process, because it is the property. Change of internal energy is the property. So it is not going to be affected by the fact whether the process is reversible or irreversible. If the end states are the same, then it is going to remain the same. That is why U2 minus U1 has been put as the same for the reversible process and irreversible process. Now subtracting equation 3.11 from equation 3.12, we get Qr minus Qi is equal to Wr minus Wi. Now the entropy change for the system is equal to S2 minus S1, and the entropy change for the surroundings, which is maintained at constant temperature, will be minus Q upon T naught. Now by the second law, we can say the entropy change of the universe, or you can say isolated system, has to be a positive definite. Now for a reversible process, we can say the entropy change of universe is equal to S2 minus S1 minus QR upon T naught is equal to 0, and this gives us the expression QR is equal to T naught into S2 minus S1. Now for an irreversible process, we can say that entropy change for the isolated system will be a positive quantity, means greater than 0. So S2 minus S1 minus Qi upon T naught is greater than 0. This gives us Qi is less than T naught into S2 minus S1. Now QR was equal to T naught into S2 minus S1, and Qi is less than this quantity. So we can say QR is greater than Qi. Now from the equation 3.13 given on the previous slide, we can say Wr is greater than Wi, means work done for a reversible process is greater than work done for a irreversible change of state. Now we want to derive an important expression that is pertaining to reversible work by an open system exchanging heat only with the surroundings. So let us consider a open system exchanging energy only with the surroundings at constant temperature T naught and the constant pressure P naught, as shown in the figure on the slide. Now a mass del mi enters the system and del mi leaves the system. A amount of heat del Q is absorbed by the system, and an amount of work del W CV is delivered by the system. And the energy of the control volume, that the system, changes by the amount dE, which is also written as d of U plus mc square by 2 plus mgz. Applying the first law, we have, so we have applied the first law, that is law of conservation of energy, and we can write del Q plus del Mi into Hi plus Ci square by 2 plus dZi is equal to Et plus delta T minus Et plus del Mi into He plus C square by 2 plus gZe. Now in the second expression, we have written Et plus delta T minus Et as d of, that is differential of U plus mc square by 2 plus mgz, because it is representing the energy of the change in energy of the system, that is dE. Now here for this system that we have considered, maximum work is equal to the work done by the control volume plus the work done by the engine. For maximum work, the process must be entirely reversible. There is a temperature difference between the control volume and the surroundings. To make the heat transfer process reversible, let us assume that a reversible heat engine operates between the two, that is, between the control volume and the surroundings. Again, the temperature of the fluid in the control volume may be different at different points. It is assumed that heat transfer occurs at points of control surface where the temperature is T. Thus in an infinitesimal reversible process, an amount of heat del Q naught is absorbed by the engine from the surroundings at temperature T naught. An amount of heat del Q is rejected by the engine reversibly to the system where the temperature is T, and an amount of work del W engine is done by the engine. Now for a reversible engine, del Q naught upon T naught is equal to del Q upon T. Del W engine is equal to del Q naught minus del Q, which is written as del Q into T naught upon T minus del Q. And finally, we get the expression del W engine is equal to del Q into T naught upon T minus 1. That is equation 3.19. Now there is important conclusion regarding equation 3.19. The work is always positive and is independent of the direction of heat flow. When T naught is greater than T, heat will flow from surroundings to the system. Del Q is positive and hence del W engine will also be positive. Again, when T naught is less than T, heat will flow from system to the surroundings. Del Q is negative and hence del W engine would be positive. Now since the process is reversible, the entropy change of the system will be equal to the net entropy transfer, and entropy generation is equal to 0. Therefore, ds is equal to del Q upon T plus del Mi into Si minus del Me into Se. Now the maximum work is equal to the sum of the system work, that is del WCV, and the work del W engine of the reversible engine. So maximum work, which is the reversible work, is equal to del WCV plus del W engine, which is written as del WCV plus del Q into T naught upon T minus 1. Now del W max is equal to del Q plus del Mi into Hi plus Ci square by 2 plus Gzi minus del Me into He plus Ce square by 2 plus Gzi minus D into U plus Mc square by 2 plus Mgz plus del Q into T naught upon T minus 1. Now as the first term on the right hand side, del Q, will get cancelled by the last term minus del Q. So we are left with del Mi into Hi plus Ci square by 2 plus Zi minus del Me into He plus C square by 2 plus Gzi minus D into U plus Mc square by 2 plus Mgz plus del Q into T naught upon T. On substituting the value of del Q upon T from the equation 3.20, what we get is del Mi into Hi minus T naught Si plus Ci square by 2 plus Gzi minus del Me into He minus T naught Se plus C square by 2 plus Gzi minus D into U minus T naught S plus Mc square by 2 plus Mgz. Now we want to deduce the expression for the reversible work in a steady flow process from the general expression that we derived on the last slide. Now for a steady flow process, as we know that the mass within the control volume does not vary with the time. So del Mi is equal to del Me is equal to del M, and also the energy within the control volume does not vary with respect to time. So D into U minus T naught S plus Mc square by 2 plus Mgz is also equal to 0. So the equation that we derived on the last slide reduces to this expression, that is del W max is equal to del Mi into Hi minus T naught into Si plus Ci square by 2 plus Gzi minus del Me into He minus T naught Se plus C square by 2 plus Gz. That is the equation 3.25. Now for the total mass flow rate, the integral form of equation shown by 3.25 becomes W max is equal to Hi minus T naught Si plus MCI square by 2 plus MGZ minus He minus T naught Se plus MC square by 2 plus MGZE. Now here the expression H minus T naught Se T naught S is known as the Keenan function. Now the maximum work is equal to Bi plus MCI square by 2 plus MGZI minus Be plus MC square by 2 plus MGZE. Now here we want to introduce one more term, that is psi, which is known as availability function for steady flow process. So psi is equal to B plus MC square by 2 plus MGZ. So on unit mass basis we can say the maximum work obtainable in a steady flow process is equal to psi I minus psi E. That is the difference of the availability function for the steady flow process for the at the state of inlet and the state of exit. Now, if kinetic energy and potential energy are neglected, equation 3.26 and 3.27 reduces to Bi minus Be, which is equal to Hi minus T naught Si minus He minus T naught Se. So, it can be written as Hi minus He minus T naught Si minus T naught Se. On unit mass basis, we can say Hi minus T naught Si plus Ci square by 2 plus Gzi minus He minus T naught Se plus C square by 2 plus GZE. Here the terms like enthalpy and entropy are written in the small letters. As you know that these extensive properties like enthalpy, entropy, they when divided by mass, they become intensive property, and they are basically written with the small letters. So this can be this equation can also be expressed in the terms of Keenan equation per unit mass, which is shown by the equation 3.29. Now, if the kinetic energy and potential energy are neglected, then the maximum work obtainable for steady flow process is the difference between the Keenan function at inlet and outlet, that is Bi minus Be. So you can write as Hi minus He minus T naught Si minus Se. This is the maximum work obtainable for a steady flow process. Now we want to deduce the expression for the reversible work in a closed system from the general expression that we derived earlier. Now for the closed system, you can say del Mi is 0 and also del Mi is equal to 0, because there is no mass that is entering the system during the process, and there is no mass leaving the system during the process. So the equation 3.24 then becomes del W max is equal to minus D of U minus T naught S plus MC square by 2 plus MGZ. Now for a change of state of the system from initial state 1 to final state 2, we can write W max is equal to U1 minus T naught S1 plus MC1 square by 2 plus MGZ1 minus U2 minus T naught S2 plus MC2 square by 2 plus MGZ2. As we know that E, that is energy, is equal to the summation of three important terms, that is internal energy, kinetic energy of the system as a whole, and the potential energy of the system as a whole. So E is equal to U plus MC square by 2 plus MGZ. So del W max is equal to minus D of E minus T naught S. So W max is equal to E1 minus T naught S1 minus E2 minus T naught S2. If kinetic and potential energy are neglected, then W max is equal to U1 minus T naught S1 minus U2 minus T naught. On unit mass basis, the equation can be written as shown on the slide by equation number 3.33. Now there is a useful term which is known as the useful work, and which is very important for the expression of the maximum work for closed system. Now all the work W of the system would not be available for delivery, since a certain portion of it would be spent in pushing out the atmosphere, as shown in the figure. The useful work is defined as the actual work delivered by a system less the work performed on the atmosphere. So we can say the useful work is equal to the actual work minus P naught dV. Similarly, the maximum useful work will be the maximum useful work is equal to maximum work minus P naught into V2 minus V1. In differential form, we can write del W max is equal to del W max minus P naught dV. This equation represents the maximum useful work done by an unsteady open or closed system exchanging heat only with the surroundings. In steady flow system, the volume of system does not change. Hence, the maximum useful work would remain the same. That is, no work is done on the atmosphere. So in that case, that is in the cases where volume of the system does not change, for example, in the steady flow system, you can say del W max, that is useful maximum work, is equal to maximum work. But in the case of an steady flow open system or a closed system, the volume of the system changes. Hence, when a system exchanges heat only with the atmosphere, the maximum useful work becomes the maximum useful work equal to maximum work minus P naught dV work. So substituting del W max from equation 3.24, we get the equation as shown by the equation number 3.38. So what is being done here? Because of the addition of this P naught dV term, we are having P naught V term in the third term of the equation 3.38. Now, for the closed system, we can say del Mi is 0 and del Mi is also 0. So, the equation 3.38 can be written as del W U max is equal to minus D of U plus P naught V minus T naught S plus MC square by 2 plus MGZ. Now, del W U max is equal to minus D of E plus P naught V minus T naught S. As we know that E is equal to U plus MC square by 2 plus MGZ. Now, WU max is equal to E1 minus E2 plus P naught into V minus V1 minus V2 minus T naught S1 minus S2. Now, if kinetic energy and potential energy terms are neglected, equation 3.40 becomes WU max is equal to U1 minus U2 plus P naught into V1 minus V2 minus T naught into S1 minus S2. This can also be written in the equation as given by the equation 3.42. So, WU max is finally written as phi 1 minus phi 2, where phi is the availability function for the closed system and is given by U plus P naught V minus T naught S. If the state of the system departs from that of surroundings, an opportunity exists for producing work. As the system changes its state towards that of the surroundings, this opportunity gets reduced and it stops to exist when the two are in equilibrium with each other. When the system is in equilibrium with the surroundings, it must be in pressure and temperature equilibrium with the surroundings. That is P naught and T naught. It must also be in chemical equilibrium with the surroundings. That is, there should be no chemical reaction or mass transfer. The system must have zero velocity and minimum potential energy. This state of the system is known as the dead state. This state of the system is designated by affixing subscript 0 to the properties. Any change in the state of the system from the dead state is a measure of the available work that can be extracted from it. Further, the initial point of the system from the dead state in terms of pressure, temperature, either above or below it, higher will be the available energy or exergy of the system. All spontaneous processes terminate at the dead state. So now we are going to deduce the expression for the availability in a steady flow system. The reversible maximum work associated with the steady flow process for a single flow is W max is equal to Hi minus T naught Si plus mci square by 2 plus mgzi minus He minus T naught Se plus mc square by 2 plus mgze. Now with a given state for the mass entering the control volume, the maximum useful work obtainable, that is the availability, would be when this mass leaves the control volume in equilibrium with the surroundings, that is at the dead state. Since there is no change in volume, no work will be done on the atmosphere. Let us designate the initial state of the mass entering the control volume with the parameters having no subscript, and the final dead state of the mass leaving the control volume with parameters having subscript 0. The maximum work or the availability of the given system A is designating the availability of that given system would be Hi minus T naught Si plus mci square by 2 plus mgzi minus H0 minus T0 S0 plus mgz0, which is equal to psi minus psi 0, denoted by or indicated by the equation 3.43 on the slide, where psi is the availability function for the steady flow system and the velocity at exit will be considered equal to 0, because at the dead state we assume that the system is at the 0 velocity and minimum potential energy that I have told you while discussing the dead state. Now this is the availability of a given system at any state as it enters the control volume steady flow process. The availability per unit mass will be del W U max is equal to del Mi into Hi minus T naught Si plus Sci square by 2 plus Gzi minus del Me into He minus T naught Se plus C square by 2 plus Gz minus D of U plus P naught V minus T naught S plus Mc square by 2 plus Mgz. So the availability per unit mass, or you can say the useful maximum work, will be equal to Hi minus T naught Si plus Ci square by 2 plus Gzi minus He minus T naught Se plus C square by 2 plus Gz, and that is equal to psi minus psi 0. So the maximum useful work, that is A1 minus A2, that is the availability per unit mass, which is equal to psi minus psi 0, will be equal to Hi minus T naught Si plus Ci square by 2 plus Gzi minus H naught minus T naught S naught plus Gz0 minus Hi T naught Si plus Ci square by 2 plus Gzi minus H naught minus T naught S naught plus Gz naught, and that can be written as Hi minus He minus T naught into Si minus Se plus Ci square minus C square by 2 plus G into Zi minus Ze. If kinetic energy and potential energy terms are neglected, then the maximum work will be equal to Bi minus Be, which is equal to Hi minus He minus T dot into Si minus Se, where B is the specific Keenan function. This subscript 0 is also sometimes spoken as naught, means I can also say P naught in place of P0. So now we will discuss availability in non-flow process. Let us consider a closed system and denote its initial state without any subscript and the final dead state subscript naught, that is 0. The availability A of the system, or the maximum useful work obtainable as the system reaches dead state, is given by A is equal to useful maximum work is equal to E minus E naught plus P naught into V minus V naught minus T naught into S minus S naught, which is equal to U plus MC square by 2 plus mgz minus U naught plus mgz naught plus P naught into V minus V naught minus T naught into S minus S naught. If kinetic energy and potential energy terms are neglected, and for unit mass, the availability becomes A is equal to U minus U naught plus P naught into V minus V naught minus T naught into S minus S naught, which can also be written as U1 plus P naught V1 minus T naught S1 plus U2 plus P naught V2 minus T naught S2. which is equal to phi minus phi naught, where phi is the availability function for closed system. If the system undergoes a change of state from 1 to 2, the decrease in availability will be A is equal to phi 1 minus phi naught minus phi 2 minus phi naught, and that can be written as phi 1 minus phi 2, which is equal to u1 minus u2 plus p naught into v1 minus v2 minus t naught into s1 minus s2. This is the maximum useful work, or this is the maximum work obtainable under the given surroundings. Many times in chemical reaction, the reactants are often in temperature equilibrium with the surroundings. Means the temperature of the system or of the reactants before the reaction has taken place is equal to the temperature of the products after the reaction has taken place. An internal combustion engine can be cited as an example of such a process if we visualize the products being cooled to atmospheric temperature T0 before being discharged from the engine. Let us consider a system which is in temperature equilibrium with the surroundings before and after the process. The maximum work obtainable during a change of state is given by maximum work is equal to E1 minus T0 S1 minus E0 minus T0 S2. If kinetic energy and potential energy changes are neglected, then maximum work is equal to U1 minus T0 S1 minus U2 minus T0 S2. Since the initial and final temperature of the system, that is T1 and T2 respectively, are the same as that of surroundings, that is T0, then we can say the maximum work at constant temperature is equal to U1 minus U2 minus T0 into S1 minus S2. The subscript T is denoting that the constant temperature is maintained constant during this process. Let a property called Helmholtz function f be defined by the relation f is equal to u minus t s. Now f1 minus f2 when temperature is constant is equal to u1 minus u2 when temperature is constant minus t0 into s1 minus s2. Thus the maximum work at constant temperature is equal to f1 minus f2 when temperature is constant. So maximum work at constant temperature is equal to the difference of Helmholtz function when temperature is constant, and the work when temperature is constant is less than equal to the difference of Helmholtz function when temperature is constant. So from there we get the definition of Helmholtz function. The work done by a system in any process between two equilibrium states at the same temperature during which the system exchanges heat only with the environment is equal to or less than the decrease in Helmholtz function of the system during the process. The maximum work is done when the process is reversible and their equality sign will hold. If the process is irreversible, the work is less than the maximum. Many times we also encounter a system which is not only in temperature equilibrium but also in pressure equilibrium with the surroundings before and after the process. Now if the volume of the system increases, some work is done by the system against the surroundings, that is PDV work, and this is not available for doing useful work. Neglecting the changes in kinetic energy and potential energy, the availability of such a closed system can be expressed as the maximum useful work is equal to U1 plus P naught V minus T naught S1 minus U2 plus P naught V2 minus T naught S2, and the availability, that is maximum useful work, is equal to U plus P naught V minus T naught S minus U naught plus T naught V naught minus T naught S naught. The maximum work obtainable during a change of state is the decrease in the availability of the system as given by the equation 3.48 for the unit mass. Now the maximum useful work is equal to A1 minus A2, which is equal to phi 1 minus phi 2. Now the maximum useful work is equal to U1 minus U2 when pressure and temperature are constant plus P into V minus V1 minus V2 when pressure and temperature are constant, minus T into S1 minus S2 when pressure and temperature are constant. That is equation number 3.54. Now, if the initial and final equilibrium states of system are at the same pressure and temperature of the surroundings, say P1 is equal to P2 is equal to P naught is equal to P, and T1 is equal to T2 is equal to T naught and is equal to T. Now the Gibbs function is defined as G is equal to H minus T into S. Now as enthalpy is equal to U plus PV, so we have substituted its value. So G is equal to U plus PV minus T into S. So G1 minus G2 is equal to U1 minus U2 plus P into V1 minus V2 minus T naught into S1 minus S2 when pressure and temperature are constant, as shown by the equation 3.56. Now we can say maximum useful work is equal to G1 minus G2 when pressure and temperature are constant, and the useful work is less than equal to G1 minus G2 when pressure and temperature are constant. So basically this gives us the definition of Gibbs function or Gibbs energy. The decrease in the Gibbs function of a system sets an upper limit to the work that can be performed exclusive of PDV work in any process between two equilibrium states at the same temperature and pressure, provided the system exchanges heat only with the environment, which is at same temperature and pressure as the end state of the system. The process is irreversible. The useful work is less than the maximum. A common measure on energy use efficiency is the first law efficiency. The first law efficiency is defined as the ratio of the output energy of a device to the input energy of a device. The first law is concerned only with the quantities of energy and disregards the forms in which energy exists. It even does not discriminate between the energies available at different temperatures. It is basically the second law, which provides a means of assigning a quality index to energy. The concept of available energy or exergy provides a useful measure of energy quality. With this concept, it is possible to analyze means of minimizing the means of consumption of available energy to perform a given process, thereby ensuring the most efficient possible conversion of energy for the required task. The second law of efficiency is defined as the ratio of the minimum available energy or exergy which must be consumed to do a task and the actual amount of available energy or exergy consumed in performing a task. So, second law efficiency is the ratio of minimum exergy intake to perform the given task and the actual exergy intake to perform the same task. A min is basically denoting the minimum exergy intake to perform the given task, where A is denoting the actual exergy intake to perform the same task. A power plant converts a fraction of available energy A or W max to useful work W. For the desired output of W, A min is equal to W and A is equal to W max. So I is equal to, that is irreversibility is equal to W max minus W. And the second law of efficiency will be the ratio of W max upon W. That is, it will be the ratio of the maximum work that can be obtained and the actual work that is done or that is required to perform the task. The first law of efficiency is the ratio of work done and the heat supplied. So it can be written as W into W max upon W max into Q, as W max is multiplied with numerator as well as denominator. So the second term on the right hand side is the Carnot efficiency and the first term is the second law efficiency. So first law efficiency is equal to second law efficiency into Carnot efficiency. So second law efficiency is equal to first law efficiency divided by Carnot efficiency. Now we want to discuss something about exergy. The energy of the universe, like mass, is constant. We know that energy is always conserved. What is not conserved is the exergy, the useful potential of the energy. Once the exergy is wasted, it can never be recovered. When we use energy, for example, electricity at our homes, we are not destroying energy. We are merely converting it to less useful form, a form of less exergy value. The maximum useful potential of a system at the specified state is called exergy, which is a composite property depending on the state of the system and the surroundings. A system which is in equilibrium with the surroundings is said to be at dead state, having zero exergy value. The mechanical forms of energy such as kinetic energy and potential energy are entirely available energy or exergy. The exergy W of thermal energy Q of the reservoirs is equivalent to the work output of the Carnot heat engine operating between the reservoir at temperature T and environment at T0. That is why we can say W is equal to Q into 1 minus T0 upon T. The actual work during the process can be determined from the first law. If the volume of the system changes during this process, a part of this work, that is work surroundings, is used to push the surrounding medium at constant pressure P0, and it cannot be used for any useful purpose. The difference between the actual work and the surrounding works is always called the useful work, WU. So U is equal to W minus W surroundings, that is W minus P0 dV. W surroundings is 0 for cyclic devices, for steady flow devices, and for the system with fixed boundaries, that is rigid walls. The maximum amount of useful work that can be obtained from a system as it undergoes a process in the two specified states is called the reversible work, that is W reversible. If the final state of the system is the dead state, the reversible work and the exergy becomes identical. The first law efficiency alone is not the realistic measure of the performance of engineering devices. Consider two heat engines having, for example, a thermal efficiency of say 30%. One of the engines A is supplied with heat Q from a source at 600 Kelvin, and other engine B is supplied with the same amount of heat Q from a source at 1000 Kelvin. Both the heat engines reject heat to the surroundings at 300 Kelvin. Now, at first glance, it may appear that both engines convert the same fraction of heat that they receive to work, thus performing equally well from the viewpoint of first law. But from the perspective of second law, the engine B has greater work potential, 0.7 Q available to it, and thus should do a lot better than engine A. Therefore, it can be said that engine B is performing poorly relative to engine A, even though both have same thermal efficiency. Now, to overcome this deficiency of first law, a second law efficiency can be defined as the ratio of the actual thermal efficiency to the maximum possible thermal efficiency under the same condition. So here you can see the second law efficiency of the engine A, which is the ratio of actual work and the reversible work. So the actual work is 0.3 Q, whereas the reversible work is equal to 1 minus 300 upon 600 into Q, which becomes 0.5 Q. So the ratio of 0.3 Q and 0.5 Q becomes 60%. Now for this engine B, the actual work is equal to 0.3 Q and the reversible work is equal to 1 minus 300 upon 1000 into Q. So the numerator is 0.3 Q and denominator is 0.7 Q, and this ratio becomes 43%. So we can say engine A is converting 60% of the available work potential, that is exergy, to useful work. This is only 43% for the engine B. This is all for the available energy. Thank you.